get back into the swing of things. Hopefully you all had a good first day back to co-op. And yeah, that's kind of what's going on. Does anybody have any questions? Anything they want to go over? When will the homework be due? That's a great question. I think we are going to finish today, which would make the homework due on Monday. Well, no, not on Monday. You would get, I guess you would get till the following Monday. So your test and homework will be the following Monday. But obviously, if you have it done this coming Monday, that would be good too. As long as we get through everything today, but I'm pretty sure we will. Anything else? All right, well, let's go ahead and get started then. If you have any questions, let me know. Oh, I did want to tell you, I went to a class last night. It was about something else, but they were having a discussion about the SAT and ACT specifically. So I thought for you ladies that are taking the ACT soon, the interesting statistic was that for the SAT and ACT, 80% of the math questions are from Algebra 1 and geometry, and the other 20% come from Algebra 2, basically, Algebra 2. So a couple things with that. One is make sure you review your geometry. And then, yeah, I just thought that was an interesting statistic. So I was like, I want to tell them that when you're studying for your ACT, go back and look at your geometry. And all of you, I think, have taken geometry, or you might have flip-flopped it with this class. So don't forget all your geometry before the ACT and SAT. Not that that's all geometry, but they have some part of that, and then a lot of algebra, obviously. Okay, so on Monday, remember we learned about logarithms, right? And the silly thing is that the log goes to the basement to find the answer, which is the exponent, right? And so basically a logarithmic function is just another way of writing an exponential function, okay? And so it's, yeah, they're just rewritten in different forms. And what logarithmic functions are really good for is helping us with exponential functions that we need to solve, which is what we're going to talk about today. Before we do, at the end of class, I don't know if you remember, I said I would go ahead and do these last few problems where we're graphing logarithmic functions. So thankfully, your calculators are pretty good at this. So if I go to Desmos and I want to graph y equals the log base 3 of x. So it's under miscellaneous, log base 3 of x. Okay, so what you'll see here is a logarithmic function. Very exciting, right? It kind of reminds you of an exponential function, but it's going in the opposite direction, right? So if I graph, I might not be 100% right, so give me a second. There we go. Yep. So if I graph 3 to the x power, which is an exponential function, remember we talked about those in the beginning, they're growing exponentially. And then if I graph the log base 3 of x, you can see that this exponential function and this logarithmic function are inverse functions of each other. So remember in math, an inverse function basically reflects across the line y equals x. So y equals x right there. This is our red line is our logarithmic function, and our blue line is our exponential function. You can see how they reflect across each other. So I think it's pretty cool. It's a visual representation of how a logarithmic function and an exponential function have this like opposite kind of relationship. This doesn't work out when you're trying to say the log goes to the basement to find the answer, which is the exponent, because if I was doing that, if I was rewriting this as the log goes to the basement to find the exponent, which is the answer, it wouldn't look like the blue one because these aren't the same functions, they're inverse functions of each other. Okay, so the whole idea of an inverse function is important because that's how we get to, when we take the inverse of something, we're basically undoing it in math. And so that's how we're able to solve, right? So at the very, very basic, if you have 1/2 times x, the inverse of 1/2 is 2. And so that when you multiply by the inverse, then you can solve for x, and the very, very basic level. Let's see. There was another one to graph, which was log of 1/2 of x. So you'll see, we'll go ahead and put that on here. Y equals the log of 1/2. Oops. Didn't like that. Maybe I'm going to have to type that in as 0.5. Let's try that again. Log of, and you guys can be doing this while I'm doing this so you can kind of see. So what happened here? So my base of my log, right, is 1/2, and look what happened in my logarithmic function. It flipped over. So this is when I have a logarithmic function that's less than 0, or less than 0, less than 1, right? And so the inverse function of that would look like y equals 0.5 to the x power. Okay, so if I clear these two other guys off, it's hard to see, but actually this purple log function and my black exponential decay function are also inverses of each other. Right? If you were a you know, crazy good at Desmos, that you could make some really cool drawings on there. Now, you might say, but Mrs. Ross, all I have to use is my TI 843 calculator, and it does not have this nice function where I can put in different base numbers. Okay, so there is something called the change of base formula, and it's pretty easy. So if you have, for example, we were going to graph, well, let's just take the generic log base b of x, okay? And your calculator can't put different bases in, right? You're taking your SAT, ACT, it can't put a different base in. You are just without Desmos, you want to know how to do it on there, whatever the reason might be, right? This is a very common formula. When you hear logarithms, you'll probably hear something about the change of base, okay? And so what that means is that I can rewrite any logarithmic function like this as the log of a new base of x over the log of the same new base, that should be like a d, of b. So what I mean by that is, in our last example, we had the log base 3 of x. So another way I could write that is I could write the log of x divided by the log of 3. Okay, and what base would I choose from this log? Well, I'm going to choose the standard base, which is 10. I'm not even going to mark it in there as 10, right? I'm just going to choose, remember, if you don't see a number here, that means we're assuming that it's 10. And pretty much all scientific calculators at least have a logarithmic function for base 10. So just to kind of prove that to you in Desmos, if I turn these guys off, go back to my original log base 3 of x, what I said was, instead, I could write this as just plain old log of x. No, what did I do there? Wow. It's like an infinite loop I had going on there. All right, I could do that. The log of x divided by the log of 3. Okay, so can you see how, let me shrink this. Actually, they're both red, but so this logarithmic function and this logarithmic function, they overlap each other. Okay, they're the same. This is just called the change of base. What makes these two different is that these are log base 10, and I don't have to have any special fancy calculator. So if I'm on my TI-84 and I want to graph log base 3 of x, I can instead type in, just hit log of x divided by the log of 3, and it'll give me the same solution. Okay? Does that make sense? You can pick any base you want, by the way. I mean, if you wanted to make it more complicated, you can make this the log of, 4 over the log of 4. I'm not quite sure why you would do that. I would pick 10, but it will work. You can pick whatever you want. The other thing that you can pick, but wait, there's more. The other thing that you can pick is, instead of just taking the log of both, you could change this to the natural log of x over the natural log of 3. That would also work. So again, if I go back to Desmos, I could do the natural log of x divided by the natural log of 3. And you can see, again, that's on top of the red curve, on top of the red curve, on top of the red curve. So really, it can be any logarithmic function, because remember, the natural log is just a log function with the base of e. So it can be any of those. So it's a pretty cool little math trick, I guess, if you want to call it that. Not, pretty cool way to deal with logarithmic functions. Okay, any questions? Make sense? You guys still here? You all huddled under blankets, falling back asleep. Cool. Noah's still here. All right. So, by the way, what is a log function? It's just a value. So, like, if you type in the log of 5, like, it's just a number. Every single, okay, great, Olivia. Yeah, every single value of, log base 5 or whatever, it's just a number, really, when you think about it. Okay, so that's what's going on with graphing. I do have a question for you guys. This had homework listed on it, and I didn't print this out yet, but did your 7.5 have homework listed on it? Anybody that has the notes, will you check and see if it has homework listed on it? Let's see. Okay, so at the end of class, I will tell you what your homework is for 7.5. I'll look it up on my notes here. Okay, so what I want to do is I want to hop into 7.6, which is our last section of chapter 7. Hard to believe. And we're going to talk about how do we actually use these, right? How are we actually going to use these logarithmic functions that you're telling me all about? So we're actually going to use them to solve equations in different ways. The first set of equations, or this first set of problems that I'm going to show you examples for, kind of like a thinking problem. So here's the general principle. If you have some base to the x power equals some base to the y power, then your two exponents equal each other. So this is pretty self-explanatory. Like if I told you, before we even get into these problems, I have 3 to the x power equals 3 to the 5th power, okay? What would you tell me x is? X is 5, right? We have the same bases that therefore, yeah, exactly, Olivia. We have the same bases, so you can just therefore tell me that the two exponents equal each other, okay? Even if we got a little bit more complicated and I had, 5 to the y power equals 5 to the, I don't know, I'm just making something up. So 2y minus 3 power, okay? My bases are the same again. They're both 5, right? So I can therefore just look at my exponents and say, oh, well, y equals 2y minus 3. That makes sense, right? Then I can go about solving that, which you're going to end up getting that minus plus y equals 3. Okay, so you can solve that. So that's the general rule that if your bases match, then you can just set the exponents equal to each other. All right. And I think that's intuitive. It's like, oh, well, yeah, that totally makes sense. What happens though when you get a problem like number 1 here? Okay. So number 1 is 9 to the 2x power equals 27 to the x minus 3 power. Okay. So can I automatically say, oh, well, 2x equals x minus 1? Does that work? The answer is no, unfortunately not, because the bases are different, right? One is a base of 9 and one is a base of 27. Okay. All right, so we got to think about this a little bit more. What could I do to perhaps make the bases the same? So I know something about 9. I know that 9 is equal to 3 squared. Okay. You may or may not know this, but I also know that 27 is equal to 3 cubed. Okay. So if instead of writing 9 to the 2x power equals 27 to the x minus 1 power, instead of writing 9 here, what if I wrote this as 3 squared to the 2x power equals 3 cubed to the x minus 1 power? I'm allowed to do that, right? I'm just changing the form of 9 and changing the form of 27. I'm good so far, right? And as long as I remember my exponent rules, so I have a power to a power here, right? This becomes 3, and then I multiply 2 times 2x, 3 to the 4x power, right? And then over here, it's going to be 3 to the 3 times x minus 1 power. So I had to do a little work, right? I had to do a little bit of work, but I'm able to get two bases that are equal to each other. And now I can ignore the fact that I have exponents, and I can ignore the fact that I have exponents because my bases are the same, and then I can just set my exponents equal to each other. So I get 4x equals 3 times x minus 1. Okay, so the two tricky parts of this, and we'll go ahead and solve that, but the two tricky parts are figuring out which base they have in common. Okay, so that's the one tricky part. The second one is remembering your exponent rules, that when you have an exponent to an exponent, you multiply them. All right, so this is 3 times x minus 1. Not 3x minus 1. It's going to be 3 times the quantity of x minus 1 and 2 times 2x, which is 4x. Okay, so then I can do a little math. 4x equals 3x minus 3, and I subtract 3x from both sides, and I get that x equals negative 3. Okay, x equals negative 3. All right, so whenever you're solving a problem, which is nice, especially like on a test, you can always check your work, right? So how could I check my work? Well, one way is I can plug it back in, right? Let me make this little, oops, it always wants to do that stuff. Where are we at? We're on this one. Oh, well, there you go. All right, so we'll get rid of all these log functions. And I just said that x equals negative 3. So if I plug it in one side of my equation, 9 to the 2 times negative 3 power. Okay, so that's a tiny little number. Does that equal 27 to the negative 3 minus 1 power? And I totally wrote that wrong. 7, this should be exponent negative 3 minus 1. I need to get rid of all this. Okay, well, they look like the same number, right? They're really tiny. So that's one way I could check. Another way you could check, or if you were doing a math problem that you needed to find out, you can always use graphing, right? Instead of putting in negative 3, you can put in x, where your negative 3 would be. So that's your original equations, right? And then I can look to see where the two intersect. In this case, it's really hard. But if I ask Desmos to find where the two intersect, they intersect when x equals negative 3. So I kind of have proven that that x does equal negative 3. Cool? Exciting stuff, right? Okay. Dun, dun, dun. Let's erase all that. Okay, so let's try number 2. Now that we kind of known what that means, let's see what we can get for number 2. Okay, so number 2 is 100 to the x, or 7x plus 1 power equals 1,000 to the 3x minus 2 power. Right? So what base, right now, do they have the same base is the question. Yep, they don't have the same base, right? What base could they have in common, though? What do you know about 100 and 1,000? These are pretty easy ones, right? Not a square. 10, right? Olivia, exactly. So instead of 100, I'm going to rewrite this as 10 squared to the 7x plus 1 power equals 10 cubed to the 3x minus 2 power. Okay, so now if I do my exponents correctly, this should be 10 to the 2 times x, 7x plus 1 power equals 10 to the 3 times 3x minus 2 power. So remember, we're an exponent to an exponent, you're multiplying, and when you have a binomial or trinomial, whatever, you have multiple terms, you have to multiply everything and make sure you distribute. Okay, so now I have both base 10, so I can ignore the fact that I have 10. It's kind of nice, right? And I can rewrite this as 2 times 7x plus 1 equals 3 times 3x minus 2. I get 14x plus 2 equals 9x minus 6. Subtract 9x from both sides. We're going to do some quick math here, right? We get 5x. Oh, we'll go ahead and subtract 2 from both sides. 5x equals negative 8. Did I do that right? X equals negative 8/5. Okay. Maybe that's a little bit over negative 1, right? It's like negative 1.56-ish, something like that. All right, so for this one, I'm going to do my quick check by, I'm just going to go straight for plugging in the two sides. So I have 100 to the 7x plus, oops, I got to put some parentheses in there. 7x plus 1. And I don't know why I have this weird dot here. Sorry. There we go. And then my other value is 1,000 to the 3x minus 2. Okay, so now I'm going to try to figure out where they intersect. And again, this is really tricky because it looks like it's going to be a really small value. Oh, here we go. I saw it on there. Okay, so they intersect when x equals negative 1.6384. Okay, if you divide negative 8 divided by 5, you're going to get negative 1.6, right? So this just shows you on here, either I typed something wrong or something went a little bit wrong, but it shows you that you're pretty close to the exact value. I think it's just approximating because it's so small, but it shows you that you're on the right track for that value. Okay. Cool. All right, now look at number 3. Yay. What's up with number 3? So I have a base of 81 and I have a base of 1/3. Does that one look fun or what? Looks like great fun, Mrs. Ross. I can't wait to try it. So let's think about what base of 81 has. So 81, you could write as 9 squared, right? 9 times 9 is 81. You can also write 81 as 3 to the 4th power. Oops, sorry, I should have written it this way. 81 is 3 to the, I don't know what's going on. I'm hitting my thing here. 3 to the 4th power also equals 81. Okay, but what about 1/3? What's another way that we could write 1/3? So remember, don't forget your negative exponent. So another way that you could write 1/3 is 3 to the negative 1 power. Right? 3 to the negative 1 power is 1/3. It's just like having your exponent in the denominator and then moving it to the numerator and making it negative. So if you see a fraction, most likely it's going to be some kind of a negative exponent that's going to help you out. Right? Had this been to the 1/9 power, then it would have been 3 to the negative 2 power, and so on. So if you see a negative exponent, or if you see a fraction, don't give up, right? Just think in your head, if it's a fraction, can I make it a negative exponent? Okay, so using that knowledge, I'm going to write this as 3 to the 4th power to the 3 minus x equals 3 to the negative 1 power to the 5x minus 6. Right? Then I need to multiply, and I get 3 to the 4, 3 minus x equals 3 to the negative 1 times 5x minus 6. Right? So then bases equal each other. I can just ignore. I'm going to go ahead and distribute when I write it down. So I get 12 minus 4x equals negative 5x plus 6. Okay? I'm going to add 5x to both sides. So I get 12 plus x equals 6. Oh, my hand keeps hitting that. Subtract 12 from both sides, and I get x equals negative 6. Right? So that's the value that will make both of my equations true. Both sides of my equations true. Okay? Pretty straightforward. A little bit of a trick to it, but not too terrible, right? Okay, so that's one set of equations. How do we solve those? We got 3 sets to get through. Okay, the next set is, what if, well, you know what? Yeah, let's go ahead and do that because the last one's easy. So this is the hardest one. Okay, let's do the hardest one and then we'll end up with the easy one. How's that sound? Okay, so what if we can't rearrange? So can we somehow, if we had 2 to the x power equals 5, right? Is there any value? Can we rewrite 5 as a power of 2 somehow? Not super easily, right? We really can't. I don't really know what 2 to the what power equals 5. So I'm going to have to do a little bit of work. So if you can't rearrange, this is where the log function can really be your friend. Okay, so you have 2 to the x power equals 5, and you want to solve for what x is. I just gave you that problem. I think we started with that problem at the beginning of the chapter. It said, how would you solve for x? And it's like, I don't know. I could kind of guess. X is bigger than 2 because 2 squared is 4, and it's smaller than 3. It's probably a little bit bigger than 2. X is probably about 2.2, but I don't know exactly, right? How am I going to figure it out? Well, if you remember kind of at the end of class on Monday, we talked about when you take let me pull it up in my notes. We talked about this property, the power property. So if you take the log of some value that has an exponent, that exponent gets to pull down to the front. So we're going to use this power property to help us out. So let me just show you what it looks like, and then it's like, oh, that's cool. So what I'm going to do is I'm going to take the log of both sides. I'm going to go ahead and just take the regular old log function. I'm not going to do any fancy base. But if I take the log of one side of my equation, I also have to take the log of the other side of my equation. Right? Has to work both ways. The reason I'm doing that isn't just to make it more complicated. It's because of this property right here, the power property, right? Which says if I have an exponent sitting up there and it's taking the log of that, I get to pull my exponent down to the front. Okay? So I get to pull this x out of my exponent, and that makes my life so much easier, right? This becomes x times the log of 2 equals the log of 5. Right? Then, if I want to solve for x, I just need to get rid of log of 2. So I'm going to divide both sides by the log of 2. And I get that x equals the log of 5 over the log of 2. So this is where you need a calculator. Again, you don't have to have a fancy calculator because I just picked the same, regular log. So if I do the log of 5 divided by the log of 2, I get that x equals 2.32, we'll round it to 2.322. Right? X equals about that. We might even do our approximately equals, right? Not exactly. So that means if I put in x up here, 2 to the 2.322 power, I should get about 5. So let's double check, right? 2 to the 2.322 power. Hear that? We get about 5. If I get even more exact with my, the more decimal places I put in from up here, from right here, the better my value gets. 9, 0, 9, 4, 8, 9. Oh, I must have rounded. Anyway, you can see you can get really close to 5 the more decimal places you put in. You don't have to write out that many decimal places. Just the first 3 would be sufficient. This is kind of cool, right? It would also have worked if instead of taking the log, what if I would have taken the natural log of 5 divided by the natural log of 2? Also works, right? Has to do with that whole idea of the ratios and the change of base. You could take the log base 5 of 5 over the log base 5 of 2 if you really wanted to do that, right? So it's not anything magical about the log base 10. It's just any, as long as you're taking the log of both sides. So now can you see how logarithms actually could be useful, right? The other thing that you can do, so this is my, so we got those two. What if I just graph this? So on one side I have 2 to the x power, and I want to know when does that equal 5? When does that equal 5? So if I go out here on my graph, here's 2 to the x power, here's 5, and they meet at 2.322. Right? So there's multiple ways that you can check your work or get to a quick solution or whatever it might be. Okay, so let's do a few more of these just to make sure, because you've never done this before, right? Take the natural log of both sides, but works pretty nicely. There we go. All right, so number 5. 7 to the 9x power equals 15. And I need to figure out what x is, right? 7, I always want to do that, guys. 7 to the 9x power equals 15. So I don't know any way to change this so that 15 is 7 to some power. I don't know how to change 15 into 7 to some power. So I'm going to use some other tool, right? This time I'm going to use the natural log just because I feel like it. So I'm going to take the natural log of 7 to the 9x power, and I'm going to take the natural log of 15, right? And what that lets me do is that lets me bring this 9x out to the front. So now I have 9x equals, or 9x times the natural log of 7 equals the natural log of 15. Okay. My tip is, since you're dealing with like crazy decimals, I wouldn't evaluate till the end. So like I wouldn't go ahead and figure out what this is, if it's 3.32 and this is 0.58 or whatever. I would just wait and do it all at once in your calculator. Okay. So what I'm going to do is I'm going to divide this side by 9 times the natural log of 7, which means I have to divide this side by 9 times the natural log of 7. That's going to get rid of my 9 that's out front. It's going to get rid of my natural log, and I'm left over with x, right? So x equals the natural log of 15 divided by 9 times the natural log of 7. So if you have your calculator, go ahead and try this because I want to make sure you get it plugged in right. Right? So we have we have the natural log of 15 divided by, and in that denominator, you want to make sure it's 9 times the natural log of 7. Okay? So we get that x equals, can't I see both at once? X equals 0.155. 0.155. Okay, so how can I check this? I can plug it back in. See if I do 7 to the 9th power times 0.15, do I get about 15? So let's try it. 7 to the 9 times, 0.1546. 29, right? So you can see you get really close to 15. It's pretty cool, actually, I think. It's like, oh, cool. I can do that. All right. Any questions about that? Pretty cool. Not very exciting. Either way. All right. So let's talk about number 6 and what we want to do for number 6. Okay. So number 6 looks like this. So number 6 has a couple things going on. We got 4. Always do that. We got 4e to the negative 0.3x minus 7 equals 13. Okay, and I want to solve for x. So you're like, oh, Mrs. Ross told me if I have x in the exponent, I'm just going to take the log or natural log and I'm done. So what you want to do before you just go straight to that is you do want to see if you can simplify your equation a little bit. Okay, so none of these were just kind of pretty straightforward, right? Here we got some extra stuff. We got a negative 7 and a 4. So let's just go ahead and clear those out of the way before we deal with the log functions, right? Because if we go ahead and do the log function like this, then it's the log of this whole big thing. And that's just, ugh, we don't want that, right? We want to be as simple as possible before we take the log or natural log. So just like in algebra, you're going to kind of go in regular order, right? So we're subtracting by 7. So let's go ahead and add 7 to both sides. And then we get 4e to the negative 1.3x equals 20, right? Then let's also deal with this 4 out front. Let's divide both sides by 4. And we get e to the negative 0.3x equals 5. Okay. All right. So that makes sense so far. So just because you see that, don't automatically think, oh, okay. All right, so now we have something interesting going on. Our base is e, right? So because our base is e, let's go ahead and take the natural log and see what happens. We could take the log of both sides and that would work, right? E is just a number. It's 2.7 something, something, right? But let's go ahead and take the natural log and see what happens. So if I go ahead and take the natural log of e to the negative 0.3x power equals the natural log of 5, one of the interesting things that happens is, well, first of all, this gets to come to the front, right? So we get to bring our exponent down. That's cool. Then we're left over with the natural log of e equals the natural log of 5. So one of the things that we didn't say exactly is that the natural log of e actually cancels each other out. Okay, so if you would type in your calculator the natural log of e, you're going to get 1. Why is that? Well, because the base of the natural log is e. So the base goes to the basement to find the answer, which is the exponent of 1. Right? So when you take the natural log of e, you just get 1. You may or may not know that. So if you don't and you went ahead and left natural log of e in there, your calculator is just going to know it's 1. But I just want to point out that that's equal to 1. Okay? So we would have negative 0.3x equals the natural log of 5, because this just is equal to 1, right? Divide both sides by negative 0.3. And we get that x equals dun, 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 natural log of 5 divided by negative 0.3. So x equals negative 5.365. Okay, so again, now I could take that and plug it way back in up here and see if I get 13, which you should. You could also graph them. Graph that. That's not what I wanted. Graph it. So you could say one side of my equation is 4e to the negative 0.3x power minus 7. And the other side is y equals 13. So we got negative 5, right? So let's see if where they connect at. So they connect at negative 5.365, which is what we got. All right, any questions about that? Think you can do it? I think you guys can do it. The last set of problems, I mean, they're going to literally take me like 1 minute to explain to you. So, that's cool. Awesome, Andon. Because I know we're almost out of time. So the last principle is that if the log of x equals the log of y, then x equals y. So an example of this is number 7. You have log base 5 of 5x plus 9 equals log base 5 of 6x. Okay, so at first this looks like a very scary equation that you have to solve, right? First you're like, yikes, I don't want to solve that, right? But since we have on both sides the log function and they have the same base, you get to ignore them and you get to just say that whatever the log is taking is equal to each other. So 5x plus 9 equals 6x. It's kind of like the exponent rule that we talked about earlier, right? If you have the same base, then your exponents equal each other. If you have the same log, then whatever you're taking the log of equals each other. And then you just solve. So in this case, you subtract 5x from both sides, and you get x equals 9. Right? Same thing here. Number 8. They're both the natural log. So I get to ignore that they're there, and I just say that x plus 19 equals 7x plus 8. And I solve and I'm done. Right? So, so that is the last section. So what that does mean is that your homework and your test will be due in a week and a half. Let me tell you what I want you to do for 7.5 homework, and then Also, on Monday, I am willing to do, like, if you guys are interested, I'm willing to do a chapter 7 review just to make sure everybody's on the same page. Sorry, rolled wrong picks. Okay, just throwing things around in here. Just to make sure you guys are all good with all of this exponential logarithmic functions. So try your homework and bring questions for me, because I am more than happy to do any questions that you might have. Okay, I'm just looking up what problems I have for you. Cool. Okay, for section 7.5, the homework is 3 through 13 odd. So not much there. So 7.5, sorry, did I say 3? I think it's 1. Let me double check. Nope, 3. 3 through 13 odd. And then everything else should be labeled on there. So I think that's it for today, guys. I hope you guys stay warm and enjoy the rest of your cold day. And thank you guys for sticking in there. But yeah, please try your homework and come on Monday. I'm willing, before we start chapter 8, I'm willing to do a review. If there's any sections that feel kind of like, I'm not quite sure, please let me know and I'm happy to do those. All right. Thanks, guys. Thanks for coming. Talk to you later. See you on Monday.